Okay, so let's look at the lines of symmetry of a square first. I think because that you should be pretty well familiar with. So it's going to be 1, because we can cut it in half, and it's going to be like a mirror up here as well. There.
One in the corner.
One in the corner, good. So there we would have 4 lines of symmetry. So this we remember from foundation phase.
Yeah.
Now, the order of symmetry is usually the same. The rotational order of symmetry is usually the same as the lines of symmetry, but it's not always. But the way you look at orders of symmetry is you think, imagine that you were to move this square to rotate it 90 degrees, right? So it'll still be a square, right? So that's,
yeah.
And then if you did it another 90, it would come.
You'd get a square.
I would get a square, and then at 270, a square,
and
a full circle.
360.
So we can rotate it. We can rotate it. Let's do it in green. 90 rotation, then another 90, then another. So it's always your maximum order of symmetry is 4. And a square is kind of perfectly symmetrical. So we rotate it 4 times. So its order of symmetry is also 4. Okay. If we look at a rectangle, how many lines of symmetry have we got?
2.
2, good.
Oh.
Yeah. Yeah, because if we cut it up there and we fold it, we'll end up like having one there, so it'll be like weird.
Yeah.
Now let's look at the orders of symmetry. So if we rotate it once, it goes like that. Twice, kind of comes back to what it was.
Yeah.
And then third time,
it goes back to standing.
Yeah, and then back to the beginning when we do the 4th time. So there we look at, we've got 2, right? 1 and 2. So there'll be 2 orders of rotational symmetry. Trapezium. Now there's an isosceles trapezium. Trapezium is the one we've drawn here, which is just one line. Yeah, so that's just
and then 2, no.
So
3, 4. No, 3.
So let's see, if we rotate it once, it's going to be kind of upside down.
Yeah.
Then it's going to be rotated again, so we'll kind of be facing this way. If we rotate it again, it's facing that way. And so it's only when it goes back, and when you rotate it the 4th time, that it goes back to its original position. So it doesn't have any rotational symmetry.
Oh, okay.
Does that make sense? Because every time you rotate it, it looks like it's a different shape.
Yeah.
So that would be 0. And just if you have a trapezium that's not a isosceles trapezium, so say it was just like an irregular trapezium, maybe like that.
You have no line of symmetry.
Good, 0, 0, yeah. No line of symmetry and no rotational symmetry. So the idea is not that you learn all of them, but that you understand a few of them and then you can work out the others. Or you could learn them all, but it's easier to understand than to learn. Okay, now here we've got no line of symmetry, right? If you try to fold it, wouldn't work here either, because it would No, this is a parallelogram, not a rhombus, by the way. A rhombus does have lines of symmetry, but this is a parallelogram. Should make
a rhombus has like, yeah, okay.
Because a rhombus is actually like a diamond, just the other way. It's just,
yeah,
it's like a diamond turned on its side. So this here, we'll just make it. We'll just write here parallelogram so we don't get confused.
Yeah, and that's like a squash down rectangle.
Yeah.
And a rectangle already only has 2 lines of symmetry.
Yeah, and this has none, right? Because so if we were to fold this here, so I've drawn the parallelogram a bit more obviously with one side much longer. And if we were folding along this line, that would kind of be there. And so we don't have any lines of symmetry in a parallelogram. In a rhombus we do,
yeah.
but not in a parallelogram. We try and draw it a bit neater just to. Okay, so imagine you draw a thing and you fold. And you fold it along this line here. It's kind of, see, it's kind of like that if you fold it along that line.
Yeah, yeah.
That doesn't really work. So we've got a zero. We've got a zero on the lines of symmetry. Let's try and rotate it and see. Okay, so imagine
you got 2.
Got 2, good, yeah. Because you're going to have
on its side, kind of like standing up, and then it'll return originally.
So it'll be like that. And then when you rotate it again, now it's back to where it was.
And then again, you get that, and then again, you
get
get
so it's back on its side, and then back to what it was. Yeah, so you got 1, and then these make another pair of, so the order of rotational symmetry on that one is 2. Okay, so the rotational order of symmetry and the lines of symmetry are different. Maybe we should do a parallelogram as well. So
parallelogram.
Sorry, rhombus.
Rhombus.
Yeah. So, but what I'm going to do to make it a little bit more obvious is I'm going to draw the parallelogram like a diamond.
Okay.
Okay, because we know that a diamond and a parallel is essentially the same thing. We've got a.
Yeah.
This is not incredibly beautifully drawn, but this should be right angles here.
Okay, cool.
So let me draw the diagonals of the parallelogram first, and then base the parallelogram on that, and then remove the diagonals. So we know that a parallelogram's diagonals bisect at 90 degrees. About like that. And like that.
This one has 2 lines of symmetry, right?
Yeah, so just by drawing the diagonals, I've pretty much drawn the lines of symmetry.
Yeah.
So if I remove it, then that's what it would be. And then if I was to draw the lines of symmetry, redo, undo. There are 2 of them, as you say. So a rhombus has 2 lines of symmetry, as you said. And then the ordered symmetry is going to be 2 as well, much like the much like the parallelogram. Okay, because these lines here are not necessarily the same, right? So these are equal and those are equal, but I can't say that, that's why I can't say that the one in red that I've done is equal to that one in red, because it's a squash down square. So the rotational symmetry is only 2 if I draw it. So it'll be, the one will be kind of look like, so we rotate it once, it's going to kind of look like that. And then if I rotate it again, it's going to look more like, well, it's going to be the same as the original. And then if I rotate it again, it's going to look like the first rotation. So these are the same. And then if I rotate it, it goes back to the beginning. So we've got 2, these 2 are the same, and those 2 are the same. So 2 rotational order of symmetries and 2 lines of symmetry. Okay, so that probably clears that up. Any shapes that you're not sure of?
A circle.
Ah, good question. Circle. So a circle has infinite lines of symmetry.
I was about to say that. Thank goodness. I thought I was a big idiot when I said that, but then I realized there's no corners.
There's no corners, so it's infinite. So they don't really ask that, but it is infinite.
And what about rotation? Is that
well, that's a good question. If you rotate it 4 times, then it would be an order of 4. Because
but when you're
it's a weird one though, because you could also say, if you could argue that it's infinite as well. Because what are you rotating? Are you rotating at 90 or are you rotating at like 0.001 degree? So
are you rotating at 100 degrees? Well, what do you want?
So what I'm saying is, if you rotate it by 90, it's an order of 4. Because the first rotation will be the same. So it doesn't matter. If you keep rotating a circle, it'll always look the same, no matter how many degrees. But assuming that we rotate it by 90, and then by 90, and then by 90, and then by 90, then it would have 4 orders. But strictly, it has infinite. Yeah. But then you could say a square has infinite as well, right? Because you could count the, you could move it 5 degrees and then another 95 degree, and I mean, and then 90 from that 5. So we can just say 4, but they're not going to ask that. It's very unlikely that they do. But do you see that by understanding how these work, you at least can intuit answer for these? Okay, cool. Let me stop there.